Okay, so we have talked about how electrons are organized around the nucleus. So now let's start talking about how they're removed or added to that nucleus, how they're added or removed from the electron cloud on an atom. So before we get into this too much, we talked about how there was a size trend on the periodic table before. We're going to add another trend to that. So another trend on the periodic table is ionization energy. And so what this is essentially how much energy do I have to use to pull an electron off an atom? How hard is it to pluck one electron away from an atom? Well, the answer is going to depend on what type of atom it is, what element it is. And so this is the energy required to remove an electron, or at least separate it from an atom. Okay, so for example, if we have something like helium, it has two electrons. They're both valence electrons. There's no inner, right? Because it just has a 1s orbital, right? It's in the first row of the periodic table. If I add enough energy, if I hit it with enough energy, I can make it into a positive cation with an electron just floating around. So I now have a helium nucleus surrounded by one electron in its cloud, and I have one electron floating freely. I've pushed it off into space. I bumper card it out of the way. And this energy, it could be from electricity. It could be from light. I could hit it with a high energy photon. So again, ionizing radiation, right? It's created an ion. That type of thing. So there's a few routes to this point. Now that's not to say that they can't recombine, by the way. Like these could bump back into each other and just become a regular helium atom again. But I'd have to spend some amount of energy to separate it, even for a brief moment. And that's the ionization energy. Now, in general, when we go up a column and to the right on a row, ionization energy increases. And so helium is actually the element with the highest ionization energy on the whole periodic table. It's in the top right. Now the reason for this is a couple of factors. Or really just kind of one factor. Well, there's actually two. So first, if we go up, remember the electron is attracted to the positive charge of the nucleus. So as we go up a column, that electron cloud, it gets smaller and smaller. So the outermost electron, that's the one we're picking off. It's going to be closer and closer and closer to the nucleus. But as we go down a row, it gets farther. And in between that outermost electron on, say, francium and the nucleus, well, look, there's 87 total electrons here. Guess what that means? This electron, between it and the nucleus, there are 86 more electrons. And they repel each other. Negative does not attract negative. They repel. So it is repulsed. It is repulsed by the sight of 86 other electrons. That's called electron shielding, because you're here and the target's here, but there's a whole mess of stuff in the way that is very shielded. There's a lot of obstacles there. Whereas, look at hydrogen. You're right there. There's no other electron between you and that nucleus. You're just, you're ready to strike up a conversation or whatever. Lithium, there's 2 in the way, but it's not bad. You're not too far away. Sodium, there's 10 in the way. That's not great. And so it's easier and easier and easier to pick off an electron because it's getting farther and farther away, and it's getting more and more shielded. Now when we go across a row, what happens to the size? It shrinks. And as the electron cloud size shrinks, that electron on the outermost part gets closer and closer to the nucleus. And the reason it shrinks is because the electron cloud isn't getting larger. The shell is, we're not adding like a new shell, but it is getting pulled in tighter and tighter because we're adding more protons to the nucleus. So the nucleus is getting more and more attractive. It's getting more and more protons. So the difference between lithium and, say, fluorine is that fluorine has 3 times the protons in its nucleus that lithium does. That's going to cause 3 times the attraction between the electron cloud and the nucleus. So it's going to pull in tighter, which means that the atom is going to get smaller, which means that outermost electron is closer to the nucleus. It's harder to pick off. It's going to have a stronger attraction. The stronger the attraction is, the harder it is to remove. And so that's why as we go left to right, ionization energy increases. And so it really just boils down to being closer to the nucleus equals higher ionization energy. So that last electron, where is it? Is it closer to the nucleus or further? That's what it boils down to. But because we know the trends of atomic sizes on the periodic table, we already know the answer to this question. If I ask you, what has a higher ionization energy, fluorine or oxygen? What am I asking? Well, I'm asking which one's a smaller atom? The answer is the one to the right. So we've actually been through this stuff before, but now I have the tools to explain it because I can talk about the electron clouds and their shells on a level of detail I couldn't before. So we've just got our, in general, 2 trends, because guess what? Just like before, this area gets a little messy. Stupid transition metals with their crazy d orbitals. So in general, there are always the exceptions. If we go up a column and across a row from left to right, then our ionization energy increases. And also in general, metals equal a low ionization energy. It's kind of a key feature for them, which means that nonmetals equals a high ionization energy. So, just something to keep in mind. Generally, it's easier to take electrons away from a metal than a nonmetal, which is why they do things like conduct electricity. Metals do, and nonmetals don't. Okay, so we can use our periodic table to talk about how easy it is to take away an electron, at least relatively between 2 elements. Like compare boron and fluorine. Well, it's going to be easier to pick an electron off boron than fluorine because fluorine is farther to the right. So it's going to be more difficult. It has a higher ionization energy. The more energy it takes, the more difficult it is. The other thing we can do is talk about stable ion charges. And to do that, we've talked about valence shells, but now we're going to really jump into full-blown valence theory. So I've introduced the valence shell. It's the outermost shell in the electron cloud. Valence theory says that shell is the most stable when it is either completely empty or completely full. So that means that chemistry essentially just boils down to filling or emptying valence shells. Well, the easiest way to do that is just add electrons or take them away. Guess what you get when you do that? You get ions. So adding or subtracting electrons can give you a stable ion if you're doing enough to fill or empty the valence shell. So what we're saying is, get this in writing, adding or subtracting. I'm on my last marker. We'll see if it makes it. I gotta get more. So adding or subtracting electrons until, so however many it takes, until the valence shell is full or empty, gives a stable ion. Okay? we saying? Well, generally it's going to be whatever. You do one or the other. You don't have the option of both with like one exception really. So like let's look at lithium. As you can clearly see, because my marker is not at all blocking that. Let's look at lithium. How many valence electrons does lithium have? Well, it's the first one in the row. It has one valence electron. Now what seems easier to you? Adding 1, 2, 3, 4, 5, 6, 7 more electrons to fill that shell? Or do you just take that one electron and dump it and you just go to 0? You just lose one electron and you have an empty shell. So add 7, lose 1. What seems like the shorter route to you? Hopefully you said lose 1. 7 is a larger number. That would be trickier. That involves working with 7 electrons, we just work with 1. So lithium will lose 1 electron, and then it has an empty valence shell, so it's stable. So lithium becomes an ion. If it loses 1 electron, what's that charge going to be? Is it plus or minus 1? Well, what's left behind is a plus. It becomes a cation. And that's a trend that you'll generally see for stuff on the left. Metals are going to become cations. Non-metals are going to become anions. These are going to add electrons, with the exception of, we're not going to really worry too much about the metals. So we're really working on the slices of bread some more. And actually not even these guys. We'll talk about those in a second. But this whole row, plus 1. Or sorry, this whole column, plus 1. This whole column, plus 2. Loses 1, 2, and it empties. Aluminum loses 1, 2, 3, it's empty, it becomes a plus 3. Plus 2, plus 1. So this column's a plus 1, this column's a plus 2, plus 3s. Transition metals, we're not going to talk about it. Now over here, what do noble gases do? Let's look at neon. Does neon need to do anything? Is there anything neon needs to do to have a full or empty valence shell? Well, it already has a full valence shell. So guess what? Neon does like no chemistry. It just doesn't do anything. It just hangs out. It's a noble gas. And helium actually has a full shell. It doesn't do anything. It's we call it inert. So you don't really do chemistry with the noble gases. These are the elements that were born with everything. All right? They live in their nice little gated community. They're like your rich cousin. You don't know what to get them for Christmas because they have everything already, or their birthday, or whatever, you know. You don't even buy them a gift anymore. You just send them a card to let them know that you know they're there, because what do you get them? They have everything. All the other elements are going to dump electrons, or they're going to add electrons, and when they do that, what they're trying to do is they're trying to be like a noble gas. The problem is the noble gases do it without ever having a charge. And so, say fluorine here, it's going to pick up 1 electron. It'll have as many electrons as neon. It's like, hey, look, you know, I am the F- ion because I've gained an electron, so I have a negative charge. I'm now the same as you, neon. And neon's like, no, I don't think so. Like, we would never let you into the tennis club with those shoes on. I don't think so. Also, you will not be invited to the tree lighting ceremony at our gated community. Like, that's not happening. Like, you live in a nice neighborhood now, fluorine. Like, you've done well for yourself. You've really pulled yourself up there. But yeah, grab hold of the bootstraps and whatnot. But no, you'll never be a neon. Because yeah, they've got it all. Like they are born on home plate. They've just got everything taken care of. So oxygen can pick up 2 electrons, become a -2 ion. Same with sulfur. So that's what we're talking about, by the way. When I say a column has similar chemical behavior, well, one thing is they're going to form ion charges similarly. This will be a -1. This will be a -1. This will be a -1. So these are anions over here. This will be a -2, -2, -2, -3, -3, -3. We're not going to talk about the middle. So that's what I'm talking about with similar chemical behavior. And so we can predict, on the edges at least, we have to talk about a whole bunch of other stuff for the middle. We can talk about the edges for ion formation. So, you know, if we look at, say, phosphorus, just to be clear about this, what kind of ion is it going to form? Well, I don't have to memorize this. I just have to look at my periodic table. I just look at phosphorus and I go, it's pretty far to the right. It's not really to the left. So it's shorter route to fill than empty. Okay. So it's going to pick up 1, 2, 3. Picks up 3 electrons. What does that mean for the charge? A -3 charge. It's going to be a -3 ion. So that's how we use yet another use for this tool, this periodic table. All right. The last thing to say about these are, well, we can talk about the electron configurations. Where are these electrons going? Where are they coming from if they're removed? Where do we add them? Where do we remove them from? Well, the answer is we just pick off the outside electrons or we add to the unfilled last sets of orbitals. So if we look at lithium, so just to be clear, we're going to talk about electron configurations now of our ions. So we're talking about the same topic, but from a new perspective. So we're not just talking about how many electrons are gained or lost, but where do they come from? Where do they go to? That's what we're going to talk about now. Well, lithium is 1s2, 2s1. Right? Okay. Lithium plus. Well, where does that electron come from? That last electron, when we empty out that valence shell, that came from the 2s orbital. So now the ion has an electron configuration of 1s2, which is the same electron configuration as helium. So it has what we call a noble gas configuration. So all these stable ions are going to have noble gas configurations. So now let's look at phosphorus. Okay. Well, we got some work ahead of us. 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3. Okay. So 1s2, 2s2, 2p6, 3s2, 3p3. P3 minus. We just peel the 3 electrons off the end. There's 3 electrons right here. We remove those. Oh, sorry. We don't remove anything, right? We're adding electrons. Guess where they go? Well, we have a half full set of p orbitals. If we add 1, 2, 3 more to those p orbitals, we have filled the valence shell. And so this should have 3 more electrons. Sorry about that mix-up a second ago. So all this stays the same. But now we're going to go 3p6. To be clear, we added 3 electrons to the 3p orbitals. And over here, what did we do? Well, we removed or lost, or had one. Maybe it wasn't given up. Maybe it was taken by another element. Maybe it was stolen. But in any event, 1 electron was lost. Oops. Removed 1 electron from the 2s orbital. All right. So that's what's going on here. So you add electrons to unfilled sets of orbitals to form anions, or you remove them. You just work your way right to left, pulling off electrons till you've lost the correct number, and you've basically emptied out all of your 2s. So the last thing I'll say is P3 minus, right? So this should be a noble gas configuration. Which noble gas is it? 1, 2, 3. Looks like it has the same setup as argon. So phosphorus like, hey argon, look, I'm just like you now. And argon's like, oh, neon told me this might happen someday. This is so embarrassing. Like, no phosphorus, you're not like me. I've always had 18 electrons, and I didn't have to steal any of them to get here. Good day to you. The doorman won't let you in next time. That's how they handle their business. Noble gases. Alright, so that's the story for this week. So we've really built it up. We've come a long way. 3 weeks in, right? We've gone from, what is matter, chemistry studies matter. Oh, we're talking about matter now big time. We are really talking about the structure of these pieces. And from here, we're going to start talking about these pieces interacting with each other. That's where we're going next. So we have told about as much of a tale as we can of individual atoms and what we can do with them. Now we're going to start having to mix them together and make compounds. And that's where we're going in the future. All right, so as always, any questions this week, let me know. I'll keep an eye on the discussion boards. Don't forget about the Chem 101 homework and quiz, all that stuff. And yeah, I'm happy to help however I can. Feel free to swing by my office hours. I'm always happy to chat. And if you want to meet and you're not available during my office hours, don't hesitate to contact me and set up a time. I'm happy to work outside of those as well. Otherwise, have fun with this stuff, and hopefully it's clicking for you.